Hello and welcome back. So, we continue our discussion of this particular problem set. So, what I did actually here, so basically I moved this one problem which we will solve now in the end, and then I have added two more problems, especially on Lagrange's undetermined multiplier. Okay. So, right now we have finished these 4 problems which are all there in the problem set. We have to finish this 2 now, and the last one I will leave it to you. Okay. So, let us start with problem number 5, which used to be problem number 4 in the last lecture, whatever I have shown you, but now I have modified it. So, it is a problem when a cylinder is rolling without slipping from on an inclined plane. Now, what is the situation here? We have already discussed the constraint condition of this particular problem, but more importantly we have to understand what is happening physically. I have added a picture also, you might have noticed. So, this is a inclined plane, this is a cylinder, this is rotating and coming down. So, it is rolling without slipping. This happens if and only if there is a frictional force, sufficient adequate frictional force which is acting on the cylinder. So, typically if this is phi, we know that the force. So, right now we are talking about the Newtonian picture of the thing. So, if the mass is m of this, so we have mg sin phi acting along this direction, and we have a frictional force which is given by Fs, which is acting in the opposite direction. Without this frictional force, in the absence of frictional force, it will just slide on it. So, there will be no practical difference between whether the mass is a cylinder or a block or a sphere or any other shape. For example, it could be this bottle also. I mean, it does not really matter, because there is no friction. It will, all the masses which will be placed here, it will come down, and only parameter we will be interested in will be this displacement x from some origin. We have to set some origin here on the top, we can also set it here, then it will be minus x, nothing other than that, and we have to look at this one parameter. But then when but now we are discussing a different situation. In the current situation, we have rolling without slipping. Now, when it rolls without slipping, that is due to these frictional forces. What we are going to do is we need to introduce a new parameter. So, this is my inclined plane, some angle phi, this is my cylinder. So, we are just looking at the cross section of the cylinder, okay. So, which has a radius r, right. So, one parameter again is this displacement x, that is there. But to account for this rotation, what happens when we are trying to write the Lagrangian of the system? We have to also add a second parameter for the angular for this rotating term. Okay. So, the kinetic energy T will now be half m x dot square, which is just the displacement plus half I omega square, where omega is the instantaneous speed of rotation and I is the moment of inertia. So, we are familiar with this part. So, this is pure rotation, this is pure translation. Now, in order to parameterize this rotation, what we need to do is, we have discussed it already, we have to take a point, any point P on the surface of this cylinder, and okay, so I will just draw it little big here. So, let us say this is the cylinder which is rolling on this this plane. So, what we do is we take any point P, or could be here, does not matter. What we do is we measure the angle from the center of the cylinder, let us call it O. We measured this angle, but for any measurement of angle we need a reference line. So, our reference line is the point of contact, which is not changing, because it is a rolling without slipping. So, the point of contact is, we can take it as a stationary, I mean, frankly speaking, it is not a stationary point. Each time a different point on the cylinder is making contact here, but we can take this as a reference point and we can measure this angle theta. So, if this is the case, then your omega will be equal to theta dot. Okay. So, what we can do is we can replace this one with theta dot square. But again, because it is a system, of one pair. I mean, it's essentially a 1D problem. So, we need to have a relation between theta dot and theta and x, and the relation is theta dot, or rather x dot is equal to r theta dot. Also we can write, I mean, this r is a constant, r is the radius. So, it will be true for second derivative also. So, we can write x double dot is equal to r theta double dot. So, these are all valid relation. So, now we can also write this, but we will take this as the constraint equation. So, this will be the equation of constraint, right, and we can rectify this as or we can rewrite this in differential, I mean in virtual displacement form as delta x minus r delta theta is equal to 0. So, we have in a general form of constraint equation is sum over lambda sum over L a lambda L q L, right, equal to 0. So, this is the generalized form of a constraint equation, where for a holonomic system the constraint equations for strictly speaking for a holonomic system, this are nothing but where the equation is given as phi of q's and time equal to 0. So, these are sorry, this is delta, sorry, there is a delta QL here. So, this are nothing but a k L will be, or this will be, or sorry, lambda L. So, this is the lambda th constraint equation. It will be del phi lambda del q L, right. But this is in case of holonomic constraint. I am just giving you whatever we have done so far, I am just giving you a recap of that. So, and in this case the Lagrange's equation can be written as d dt of del L del q k dot minus del L del q k is equal to sum over lambda, or sum over just a minute. So, it will be sum over. So, basically we have to take these, or I know by mistake I should write alpha here, that makes little more sense. If I replace it with alpha, right, this is okay. So, lambda alpha, lambda alpha a alpha n, right. So, sum over alpha, right. Now, this makes more, and this we have discussed already. This is the form. See, for a constraint of holonomic in nature, a L lambda else can be represented by this, but in case if the constraint is not non-holonomic also, this is the general valid form, most general form. So, we write this as the most general form of constraint equation, and eventually this is also the most general form of Lagrange equation with undetermined multiplier. So, now we are going to apply this equation in this particular case. Also, we have to write the potential energy equation. In this case, it will be if this, the total length, if from here to here the length of the platform is L. So, it will be simply m g L minus x sin phi, sin phi, right. So, the height will be, so instantaneous height h will be L minus x sin phi, right. So, this is now where we start, and then we have to, what we need to do is we need to follow the basically we need to construct the Lagrangian, which will be t minus phi, which will be given by L is equal to half m x dot square plus half I theta dot square minus m g L minus x sin phi. Once again, theta is a cyclic coordinate. It does not appear explicitly in the Lagrangian, which only comes as theta dot, and also this I for a cylinder which is rolling around its axis, it will be half m r square. That we have seen during our discussion of rigid dynamics, right. So, everything is there. So, all we need to do is we need to find out, see there will be two differential equations to begin with, one for x, one for theta, but using this constraint relation we can get rid of one differential equation. So, we will see in a moment that solving this problem actually we do not need to determine the Lagrange's multiplier alpha. Okay. Right. So, okay, we do not need this here because this is not a general holonomic problem, but what we can do is we can compare. So, we have only one constraint equation. So, there is only one alpha we need, alpha equal to 1 all the time, only one equation. So, there is no summation over alpha here because there is only one equation, but what we have here is we can calculate a x, the parameter a corresponding to x, which we see is equal to 1, and the parameter corresponding to r will be equal to minus r, or rather theta, sorry, not r, theta. So, we have the coefficients from this constraint condition. From here we get these two values of a and r, right. So, now I will give you a demonstration on how to write the Lagrange equation. First, we have to write d dt of this equation for x. So, d dt of m x double dot, simply speaking it will be m x dot square will be m x double dot minus, see for the second term we see if I eliminate the constant quantity m g L from this, which will not contribute anyway. So, it becomes plus m g x sin phi. So, there will be 1 minus m g L sin phi, which is a constant term, which will not, with just a constant shift of overall energy, and we are just getting rid of this, right. So, if we do that, the second term will be minus m g sin phi, okay. And on the right hand side we have to put lambda, that is the Lagrange's undetermined multiplier, times a x is equal to 1 in this case. So, we just leave it like this, right. And for the second equation, once again it will be 2. So, it will be I theta double dot, right, I theta double dot will be not equal to 0, but equal to lambda times. So, it will be basically lambda times a x, and this will be equal to lambda times a r, and we have seen that lambda times a x is equal to lambda, it will be equal to minus lambda r, right. Clear? Now, if we substitute for I here, it will be half m r square. So, we cancel 1 r from both sides, right. So, this gives you straightforward two relations. The first relation is m, so from here m x double dot minus m g sin phi is equal to lambda, and the second relation from here is m. So, what we can do now is we can simply replace r theta double dot is equal to x dot, because at the end we need only one relation, right. I mean this is the equation of single parameter. So, m x r theta dot is equal to m x double dot half is equal to minus lambda, right. So, we have this two relations, let us call them 1 and 2, and that is where we stand. So, one way of just to solve the problem would be, okay, so I am getting rid of this, I hope it is clear. So, one way of solving the problem would be just eliminate lambda from these two equations, which is very easy to do. What we can do is we can, lambda is equal to minus of that. So, we can simply write m x double dot 3 by 2 minus m g sin phi equal to 0 using the second equation, because we just put the value of lambda which will be equal to minus m x double dot by 2 and change the side. So, it will be plus and m cancels. So, we get x double dot is equal to 2/3 g sin phi, and this is our most familiar result. Just anyway, let me verify, because I have a tendency of doing things wrong. Oh, great, I have done it right. Okay. So, this is our very standard expression for, standard answer for this problem. We all know that the acceleration in this will be 2/3 g sin phi. Now, you can ask me why we need Lagrange equation in that case. Why we need Lagrange equation and Lagrange multiplier in that case. We can just reduce everything in a single parameter equation, even the Lagrangian, and solve it. In principle, we can do that, but now we will see why we need that, because now let us do one thing. From the second relation, let us determine the value of lambda. So, lambda will be minus half m x dot, right, x double dot, just put 2/3 g sin phi. So, that will give you lambda is equal to minus 1/3 m g sin phi. Now, the generalized equation what I wrote, the right hand side can be taken as generalized forces which will not be, which was not possible to be included in the Lagrangian. In this case, these generalized forces, one of them has to be the force of friction. So, we compute A x lambda, which was the right hand side, which is the right hand side of this first equation. Okay. A x lambda, now A x was 1, right. So, A x lambda is exactly the same, it will be 1/3 m g sin phi. And what is this? This is the force of friction which is acting in this particular direction. So, this is exactly equal to frictional force F s. Okay. So, this is force of friction. Okay. Sorry, you cannot, force of friction. And then we have the second parameter, which is we removed r from here, cancelled r, but it will be lambda minus lambda r. Okay. So, when we write A r lambda, which is minus lambda r, there is a minus sign already here. Okay. So, when I include this minus, it is nothing but 1/3 m g r sin phi. What is this? This is the torque of this particular force which is causing this rotational motion. Okay. So, this is the torque by friction. So, you see, using Lagrange's multiplier, when we determine lambda and put it back into this equation in order to, relation in order to get the generalized forces, we gain lot more insight than if we see, just to get to this equation, what we can do is we can reduce it to one parameter equation and get one parameter problem and get the equation. But that is not the point here. We all know the solution, how it works, but using Lagrange's multiplier, what we can do is we can actually find out the forces of friction and the torque which is causing this rotation to take place. So, it offers us something more than just getting into the giving us the equation of motion, right. Okay. So, this is what we have learned. Now, we will go to the next problem. Okay, so, the next problem is a particle moving inside, particle of mass m moving inside the paraboloid, and the paraboloid equation is given as x square plus y square is equal to a x, right. Now, we have to first set up the Lagrangian using cylindrical coordinate systems, and then we have to use a method of Lagrange's undetermined multiplier to obtain the equation of motion. Okay. So, here we are exactly, frankly speaking, we are not solving the problem here, but what we are going to do is we are going to use Lagrange's multiplier, because once again it is a 3 parameter problem. We, in order to describe the motion completely, we need 3 parameters x and y and z, but there is a constraint condition that the particle must move on the surface of this something a bowl like shape, right. So, there is an equation here. So, it has to move on this surface. So, that is the constraint condition. Now, how do we do that? First of all, what is a paraboloid? Paraboloid, just in case if you do not know, let us assume that we have x axis here and we have z axis here. So, this is a parabola, we know how a parabola looks like, it is a 2D object. Now, if I rotate this parabola, it will form, it will start around z axis, it will form a surface, right. I mean, a surface of evolution of this parabola, this arc will be a surface, and this surface is called a paraboloid, which has the following shape. Forget about rotation now. So, this is our paraboloid. So, we have, okay. So, in right handed coordinate system, this is your x axis, y axis and z axis. So, first of all, the equation of this paraboloid is x square plus y square is equal to a z. Now, we can, when we are switching to polar coordinate system, cylindrical polar is only the 3D extension of plane polar coordinate systems. So, the length elements are r, I mean 3 parameters are r, phi and z. Okay. We can also write r theta z, that is, but typically phi is more commonly used. Now, in this case x square plus y square will simply be equal to r square. Okay. So, the constraint condition might as well be written as r square equal to a z. I am not writing the explicit form of y, how x and y and are related to r and phi, it is the exact same as we have already known in the plane polar coordinate system. Only thing is there is an additional z which was not there. So, it will be r square equal to a z. Now, if I reduce it, now if I take the virtual write it in virtual displacement form. So, this is the constraint. So, we can write it as 2r delta r minus a delta z is equal to 0 in this form, right. So, in similar manner we see, so comparing with this a l k q k or a alpha k q k equal to 0, comparing with this form, we see that a r is equal to 2r and a z is equal, or a phi is equal to 0. There is no phi dependence into this equation, and a z is equal to minus a. To avoid confusion, what we can do is we can make it capital and a and z. Very good. So, this is the constraint side. Now, for the kinetic energy and potential energy, kinetic energy T for this particle is simply half m. Now, for r theta or a plane polar coordinate system, we know that the general velocity expression is r dot square plus r square, not theta dot, we have to write phi dot square. Now, it will be simply another z dot square term, and potential energy will simply be V is equal to minus mg z, right. So, we get the Lagrangian straight away. So, the Lagrangian will be, I am not just modify this a bit, minus mg z, right. So, this is my Lagrangian. So, the Lagrange's equations will be, I will use this part of the board. Okay. So, it will be d dt of del L del r dot minus del L del R will be equal to lambda AR, right. Once again, there is only one equation of constraints, so we need to use one lambda. There is no lambda, I mean, there is not many to deal with. Okay. So, if we do that, it will be m r double dot minus, right, 2, so it will be m r phi dot square, right, equal to 2r lambda or 2 lambda r. So, this will be equation 1. Similarly, I will just write the equations just in order to save time. Am I right? Yes, it is good. Second, so once again the phi is a cyclic coordinate, phi does not appear in Lagrangian explicitly. So, it will be m r square double dot, or sorry, not theta, phi is equal to 0. This will be 2, and the third equation will be m z double dot minus m g will be equal to minus lambda a, right, a minus m g. No, sorry, this will be a plus sign here, z double dot, how is it, plus, there is, yeah, so there will be a plus sign here, right, m g z is equal to minus lambda a, right. So, this is my equation 3. So, right now we have to stop here, because this is all which has been asked in this problem. I will probably will get more into your assignments, but this will be easy. Whatever you get, once you have these equations derived, rest will be easy. So, you have to, you can, using these equations, once again you can eliminate lambda, you can calculate lambda, you can do many things, right. Of course, you have to use the constraint equation. This equation is there, keep in mind. Okay. So, with this we leave this problem and we close this assign. Oh, by the way, there is a third problem or last problem which I am not doing for you, you have to do it yourself. Why I have added this problem? Because please understand this. Lagrange's multiplier, although it started off as a tool in classical mechanics, it is widely used. It is used in mathematics, it is used in statistical calculus, it is used in economics, So, the I will give you few more examples, although also you can use it in algebra, for example. Let us assume that you have to find out the intersection between a plane and a sphere or any 3D shape. Let us take it as a sphere. What is the situation we have in 3-dimensional world? A sphere is this, right, and a plane will be something like this. So, when they intercept, right, so the point of interception will be a circle, right. I hope you understand what I am trying to tell you. The intersection between a sphere and a plane has to be a circle. So, the problem is a geometric problem, let us say, but we can give it this following form. We can write the general equation, or rather I am not sure if it is in the proper origin, if it is 0. So, what we will do is we can write x minus x 0 square plus y minus y 0 square plus z minus z 0 square is equal to s or r square. So, this is the equation of the sphere, right, and an equation of the plane is given by a x plus b y plus c z minus d is equal to 0. Okay. So, we can treat this function as f of x y z, and we can treat this function as g of x y z. So, we have to solve for solve this two equations simultaneously. A very similar thing is given in. What is the way of doing it? Way is you have to include a Lagrange's multiplier into this problem, and the procedure actually is described here. If you just read Lagrange's undetermined. Okay, so the constraint condition in this particular the problem I have described in the geometric problem, it is given as the G, whatever G is equal to C. This is the equation of the plane, and variable, the main equation is given as f x y z is the equation of the sphere, right. So, you have to construct a function capital F, which is this minus lambda times this, okay. By the way, this star is the multiplication only, and then what you need to do is this f is a function of x, y, z and lambda as well, right. So, you have to take partial derivatives with respect to x and y and z and lambda. In order to gain optimal solution, if we are looking for optimal solution, we have to optimize the that big f function, right. So, if we can optimize it with respect to all 4 parameters in this particular problem, for example, we have only 4 parameters. I mean, we have 3 parameters x, y and z. The moment we construct this capital F, which will be f minus lambda g, okay, we are actually including a new parameter. So, capital F will be a function of x, y, z and lambda. So, in order to get the interception, which is this yellow circle, to get to that particular solution in this particular case, we have to optimize the function capital F with respect to x and y and z and lambda both, and in order to optimize, we have to put the partial derivatives equal to 0. So, this is a very standardized method. I am pretty sure many of you are familiar with it, because nowadays this has taken place and made its way into some of the school textbooks also. So, this is a technique called Lagrange's multiplier. In general description, if I have a function space, I mean in general space, we have a function here and we want to optimize the value of this function with respect to a constraint condition, which is given by this. So, we have to take, for example, these two intercept points, right. Okay, I mean I am just writing it in 2D, it could be a 3D contour also, okay, 3D contour and a plane. So, there could be in order to get to this solution, we have to simultaneously satisfy two conditions. One is this equation, which is given by f of x, y, z this, and another is this equation, which is given by g of x, y, z, right. Okay. So, this is what we have to do mathematically speaking, but if you think this is more complicated, stick to this particular simple geometric description. Anyway, so I am leaving this last problem up to you, and I will end this class by adding a very short description of variation principle. Now, what is variation principle and how it is applicable, I will do that in the next, I will cover that in the next lecture. But before we go there, very quickly, let us assume that we have a TQ space. So, that means in the x axis we have time, which is the independent variable, and y axis a system is moving. If a system is moving, its coordinate change as a function of time, we all know that. Now, we have all the let us say the system, okay, let us take a simple system which has only one generalized coordinate. Now, in order to track the trajectory, in order to draw the trajectory, what we can do is we can trace q as a function of t over a period of points. Now, let us take one starting point A, which is given by q t. Now, if I make a very small, infinitesimally small displacement, real displacement in time, so this point B will have a coordinate of q t plus delta t. So, the idea is from going from A to B, we have not traveled along the q axis. So, the coordinate remains same, we have just evolved little bit in time. Similarly, but now let us say if I want to represent a virtual displacement in the same diagram. Let us say there is a virtual displacement. Please remember that virtual displacements, during a virtual displacement there is no time elapse. So, a virtual displacement will be a vertical displacement. Let us say this is point C, and the coordinate of point C will be q plus delta q and t. So, in order to finish this diagram, I take the diagonally opposite point in this rectangle, which I call point D. What will be the coordinate of point D now? Okay. We know coordinate of point A, B and C. Okay. So, we will start from here in the next class, and we will build up what is called the calculus of variation.